Well, good morning, you guys. I thought I'd make you a quick video here about Hess's Law and just how to use it for your lab that's coming up due on Thursday. I know most of you might have already done it, but if you watch this and maybe have some corrections to make or whatnot, then you can go ahead and do that. Anyway, let's just do a quick overview of Hess's Law. Remember in Chapter 6, we studied thermochemistry and the enthalpy of reaction. Remember, an enthalpy of reaction is the heat exchange that occurs when reactants are converted to products. Now, in this picture you're seeing in front of you here is an example that when a reaction occurs, there can be enthalpies associated with different steps. The overall reaction for this picture, it looks like here, if you check out the top, we have carbon graphite being converted to directly carbon dioxide. Now, that is a combustion reaction, carbon burning in oxygen to make carbon dioxide, that's true. But there are certain steps that it can take. Now, it could possibly, as it's burning, be converted to carbon monoxide first with some extra oxygen left over, and then that carbon monoxide can continue to react with oxygen to make carbon dioxide. Now, who's to say that it didn't do those steps, or who's to say it didn't do the whole step? But the point is if we do know one of these individual steps, as pointed out here, you don't have to know the whole. You could use them to figure out what the whole enthalpy is for the reaction. So Hess's law states basically when reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. So what does that mean? That means we can use these and write them out like mathematical equations and flip them around just like we did in algebra. So let's check this out as this goes along. This reaction you are seeing now looks like the very first step with an enthalpy of negative 110.5 kilojoules. This next step is the second step on the figure, which is carbon monoxide continuing to react with oxygen to make carbon dioxide. Now, if you take a peek at these two reactions, you'll see that carbon monoxide is what's called like an intermediate. That intermediate is created but then reacts to make the final product. If we add these two up, you'll see those intermediates cancel out as I'm crossing them out in red. And then your overall reaction is carbon graphite reacting with oxygen to make carbon dioxide. So if we wanted to, then we can add these enthalpies up of the individual steps. We have an enthalpy for the first reaction, and we have an enthalpy for the second. And then we can add them up to get the overall enthalpy. Another way to do this or utilize Hess's law is to determine an enthalpy of an intermediate step given the total enthalpy in one of the steps. So now let's do another example utilizing Hess's law. This is one out of your textbook. And the goal is just, given these puzzle pieces, can I figure out an overall reaction? Now you're asked for the standard enthalpy of formation of carbon disulfide liquid. And you're given these puzzle pieces because for some reason you can't figure this one out directly for some reason or experimentally. So what is this, this reaction they're asking you for? The standard enthalpy of formation for any substance is the elements creating the product. So here's carbon disulfide liquid. Now, if you take a peek at what they're giving you S. Here's S. They're giving you carbon. Here's carbon. They're giving you carbon disulfide liquid. Here's carbon disulfide liquid. So here are our pieces of the puzzle hidden in these chemical reactions. Each one of these chemical reactions have an enthalpy. So if we can play with these chemical reactions such that when we add them up, we end up with this target reaction at the top, we can then use the enthalpies given over here to figure out the enthalpy of the target, which is up here. So let's check it out. The enthalpy of formation for carbon disulfide is just as I was written up there, but notice this one's balanced, which it needs to be balanced. Now notice there's up here, there is not a 2. We're going to have to fix that. Add the given reaction such that the result is desired. Now that's the overall idea of Hess's law, but we have to do some manipulation of those individual reactions. So there's our graphite. So since I wanted graphite as a reactant, this very first reaction, we'll call them reaction number 1. This is reaction number 1, stays as is. We don't multiply it by any coefficient or anything because there's a 1 in front of the carbon and there's a 1 in front of the carbon. All right, so that, now we have to look at our rhombic sulfur. Notice the rhombic sulfur is up here in reaction number 2. It is a reactant. Now it is a reactant here also, but now we had to multiply this whole reaction by 2 as well as its enthalpy to make sure that when we add our reactions up that we end up with our target. That's why now let's look at carbon disulfide. Carbon disulfide is a product as circled in red, but in our given reactions it's a reactant. So that means we have to flip it. So we flipped that puzzle piece and now our carbon disulfide is on the right, which is where we needed it to be. But we had to change the sign of our enthalpy of that reaction. So now it's in the right place. So now if we add them all up, we should, after canceling the intermediates in these chemical reactions, we should end up with our target reaction. And that target reaction is that enthalpy of formation of carbon disulfide liquid. Now to figure out the enthalpy of it, now we can just, what do we do with these? We add them up. And now we get a positive 86.3 kilojoules. That's an endothermic reaction for the enthalpy of formation of carbon disulfide. So that is Hess's law. You can play with Hess's law with all different chemical reactions, and it enables you to figure out the enthalpy of reactions that you may not be able to figure out experimentally. So for your online experiment, the goal is to run 3 reactions. The reaction of solid sodium hydroxide to create sodium ions aqueous and hydroxide aqueous. That just means dissolving. And this is an exothermic reaction. If you ever do this in a lab, it gets very hot. The next one is a solid reaction of solid sodium hydroxide with aqueous hydrochloric acid. So again, we're just playing with puzzle pieces here, but this is also an exothermic reaction. And then our third reaction is taking basically your sodium hydroxide and hydrochloric acid. It's a neutralization reaction to make water and salt. And you already did an experiment like this and knew it was exothermic. So the goal for this online experiment is to run these 3 reactions in that virtual lab and then measure the heat given off by each reaction. And we're going to convert it to a per mole of sodium hydroxide basis. Then the goal is to utilize this reaction, number 1, and number 2, by flipping it or doing whatever you need to do as far as Hess's law is concerned, such that when you add it up, you can determine the enthalpy of neutralization for reaction number 3. This is what your virtual lab looks like. It's a little desktop thing, comes out of, it's called the Chem Collective out of Carnegie Mellon University in Pittsburgh, Pennsylvania. So the goal here is you can go to this little desktop and you can grab different reagents. You can mass things out. Here's some sodium hydroxide. You can even tear your little balance. And then you can mix things together so you can measure the temperature change. Just make sure to watch. I'm such a goofball and I always forget to notice the initial temperature and I have to rerun the whole thing. Notice your initial temperature before you mix things together or whatever. And then the goal is to determine the initial temperature, see over here, and the final temperature of each reaction, and then to calculate the energy released. And remember from chapter 6, Q equals ms delta T. The mass, now it depends on which one you have here. Now remember, mass is normally the mass of the water. Now, because you can get over here, you can get a little styrofoam cup, and then you're going to end up putting things in that cup. And the mass is the mass of the water, not the mass of the sodium hydroxide. And we have the specific heat of the water, which is that 4.184 joules per Kelvin mole. So 4.184 joules per Kelvin mole. So then you can figure out your heat released for the amount of sodium hydroxide and the amount of water that you put in there. Then after you've run 3 experiments, heat released, calculating the heat released for each one of them, you want to use your moles of sodium hydroxide, either from the molarity because sometimes you were mixing aqueous sodium hydroxide, or sometimes you were using solid. And then your molar heat of reaction, you're going to determine by dividing the heat of reaction by the moles of sodium hydroxide. Because if you remember on your balanced chemical reaction, it was 1 mole of sodium hydroxide each time. So go ahead and complete that table. If you have questions, I encourage you to go to this discussion board. The discussion board is there to help you. Now I wanted to show you one more example here of the direct method. Now this is just a general example out of your textbook. When you run a reaction, how to do the standard enthalpy of a reaction using the direct method, which is using Appendix 2 in your textbook. So in this example, benzene is being burned to make carbon dioxide and water. This is a combustion reaction and it's balanced. The question is how much heat is released per mole of benzene combusted. Now notice this is 2 moles of benzene. So the standard enthalpy of formation of benzene is given to you here, but you can go to Appendix 3 and get the rest. Now recall the standard enthalpy of formation of elements is 0, so we know that one for oxygen. And remember, this is the formula that we use for our direct method. So we need to know the heats of formation for the products, the heats of formation of the reactants. And I can get those from Appendix 2. Multiplying them by their stoichiometric coefficients, I get a heat of reaction for this one of negative 5,946 kilojoules. But remember, this wanted it to be per mole of benzene. So we need to divide it by 2. So this is per mole of benzene. So doing a direct method example, I asked you to do that as a post-lab question for this virtual online lab. It turned out that sodium hydroxide solid was not in Appendix 2, and so I have posted that in the discussion board in the instructions for you to use to determine those enthalpies of reaction from the appendix. So if you have any questions, please go to the discussion board. Otherwise, I look forward to seeing your reports.